Hello and welcome to my new video. Today we discuss little bit further about the residues. So what is the next? We learn how to solve the integrals with the help of residue theorem. And one more definition I will give you here, Cauchy's integral formula. What is Cauchy's integral formula? If function fz, what we learned already, is an analytic function of z and f dash z is the continuous at each point within and on the closed contour. If we have this our region C, then it will be analytic within region and on this boundary. Then we can say Cauchy's integral formula given by integration C fz dz equal to 0. If C is divided into many parts C1, C2, C3, then the sum of all integrals is also equal to 0. One more thing, if fz is analytic function of z and A be the any point lying within C, then fa is given by this integral 1 upon 2 pi iota integration of C fz upon z minus a dz. So now we approach to the integrations. So let us see. Evaluate the following integral using residue theorem. Our integral is C 1 plus z upon z 2 minus z dz, where C is circle, modulus of z equal to 1 means circle with radius 1. So there this given this our closed curve is a circle with the radius 1. So z is first we have to, for finding the value of this integral, we have to find the poles. We have to find the poles, how many poles are, which type of poles are there. They are lie within the circle, outside within, because we consider only the on the circle and lie within the circle. So for the pole, what we can say, we use the integrand and denominator equate equal to 0. So then the finding the poles, our solution is taking the integrand and denominator z 2 minus z equal to 0. It gives the two poles z equal to 0 and z equal to 2. Both are simple poles. So both are simple, but one thing, z is equal to 0 lying within the circle, modulus z is equal to 1, but z is equal to 2 is outside. So for outside we don't work on it, we don't consider it. So only we can say z is equal to 0 is a simple pole lying within this circle. Hence we can find the residue with the help of residue theorem at z is equal to 0. So further, hence the integrand of analytic function at all point inside modulus z is equal to 1 except z is equal to 0 is given by the residues theorem mod integration of C 1 plus z, z 2 minus z dz is given by 2 pi iota residue of f0. This we learn in the residue theorem. This integral is equal to residue of f0. So our work, if we find the residue of f0, multiply with 2 pi iota, solution of this integral will come. So what is residue? Residue of f0 is given by limit z tends to 0 because it is the pole of order 1. So z fz is this function. I substitute here limit z tends to 0 z 1 plus z upon z 2 minus z. Z cancel with the z. Now we apply the limit z tends to 0. When we apply z tends to 0 here, our result become 1 by 2. So residue at f0 is given by 1 by 2. I substitute here value of this 1 by 2. So it becomes 1 by 2. 2 cancel. So what is the solution for given integral? For given integral, c1 plus z, z 2 minus z dz, where modulus z is circle 1 is given by pi iota. So this is a working how to solve the integration with the help of this theorem. One more example on the same. Evaluate integral within closed contour C z minus 3 z square plus 2z plus 5 dz, where C is the circle. Which circle? Modulus of z plus 1 minus iota equal to 2. So C is given by this circle. So step 1, first we have to dig in, or we have to find in all the poles of the given integrand. So using integrand, using the denominator and find the poles. So for finding the poles, z square plus 2z plus 5 equal to 0. So when we solve, its b square minus its roots are coming minus 1 plus minus 2 iota. So there are the two poles, minus 1 plus 2 iota, minus 1 minus 2 iota. So minus 1 plus 2 iota lies within the circle given by this, and the minus 1 minus 2 iota is not lies within the circle. So we can consider only minus 1 plus 2 iota. How to decide? Because so we can see minus 1 plus 2 iota. Minus 1 plus 2 iota lies within the circle, but minus 1 minus 2 iota is not exist inside this circle. So we using only this pole for finding the value of this given residue. So now using this pole, what is our residues theorem say? Residues at f minus, using residue theorem. What is our residue theorem? Residue of fa is given by limit z tends to minus a, z minus a, fz. So we can, using where our a pole is minus 1 plus 2 iota. So residue f minus 1 plus iota, limit z tends to minus a, z minus of minus 1 plus 2 iota into fz. Fz is z minus 3 upon z square plus 2z plus 5. So our integral becomes this. Next, simplify it. When we simplify, we can open. This becomes z minus minus plus 1 minus 2 iota. When we break it, it also z plus 1 minus 2 iota, z minus 3, and denominator also become z plus 1 plus 2 iota and z plus 1 minus 2 iota. Clear? So this will be cancelled out. Now apply the limit. When we apply the limit, z is equal to minus 1 to iota. At the place of this you put z equal to minus 1 plus 2 iota. So you will get the solution minus 4 plus 2 iota upon 4 iota. Now remove the iota from the denominator, multiply and divide by iota. So finally we will get iota plus 1 by 2. So solution of this given integral is integral c z minus 3 z square plus 2z plus 5 dz is given by 2 pi iota of residue of that point is iota plus 1 by 2.